Okay, I should be able to see the introduction screen. Let me know if you guys can't see it there. Introduction to navigation. So my name is Lieutenant Shaw. This one class here is going to be a little bit longer than normal, just because there's a lot to cover in Introduction to Navigation. So Colin from Calgary. I'm the Vulcan Cadet Flying Site Officer in charge. So the Vulcan CFS is south of Calgary, near the town of Vulcan. I was a cadet at 107 Spitfire in Saskatoon once upon a time and did my flying training and international air cadet exchange quite some time ago. Civilian life, I'm a pilot at WestJet. Um, so those two pictures, one of them was when I used to fly medevacs. That's in Clyde River, Nunavut. And the other picture that's a friend of mine that I did glider with. We happened to both be landing in Regina at the same time doing our walk around. So we got a chance to meet and high five and take a picture and go back. He flew back to Toronto and I flew back to Calgary on the Dash 8. Getting right into it. I've got a lot to cover in this class. So we're going to talk about longitude and latitude, identify and relay grid coordinates, describe the difference between a rhumb line and a great circle. I'm going to talk about true magnetic and calibrated headings, same with conversion between true magnetic and calibrated. Describe the difference between bearing and heading, 1 in 60 rule. We're going to talk about map projections and the different charts and navigational aids used in Canadian aviation. Brito, you have a question? Or did you just forget to put your hand down?
Sir,
Yep.
before we begin, can you make it so that we can have access to changing the slides so that we can see them on our screen differently so that we can copy the notes better?
Goodness, I'm not sure how to do that, to be honest with you. Yeah, I'm not sure how to do that. If there's something that you want me to review, then I can certainly go back and do it, but I'm not 100% sure how to do that. I can maybe try and look at that in the break if that's okay. Yeah, if there's something you want me to go, I'll try and go through it here, but we do have quite a bit to cover today. It'll take up most of the time, so I'm sorry I couldn't be more help. I'll try and look up how to do that during the break.
No problem.
Hopefully you're able to see the main teaching point slide here now. So we'll start off with longitude and latitude. So imaginary lines that make up a grid on the surface of the Earth. So the parallels of latitude run east to west, like the equator, and are numbered 0 to 90 degrees north and south from the equator. And the meridians of longitude run north to south and are numbered 0 to 180 degrees west and 0 to 180 degrees east from the prime meridian. So the prime meridian, you might recall, is 0 degrees. That runs right through Greenwich, England. So that's right, basically just outside of London, England. So the prime meridian always runs right through Greenwich. Some things to talk about. So meridians of longitude, they converge towards the poles. So they come together. They kind of start off at the north and south pole and they spread out as you go over the surface of the Earth. Parallels of latitude, as you might recall from the name. So parallels, they run parallel to each other and they don't converge, sorry, they don't ever touch. Another way I like to think about it is latitude, fatitude, which I know we're all about body positivity, but that's just the easiest way for me to remember. Fatitude meaning kind of a latitude around your waist. Or if you played football, lateral or latitude, kind of like a lateral, so like a sideways pass. There's a few different ways you can kind of remember it. So parallels of latitude are like rings around east to west, and they're parallel, so they don't touch. Whereas meridians of longitude converge on the poles. So because of that, there's a couple things we got to do. Latitude is measured in degrees, minutes, and seconds, and includes north or south. So remember the equator for parallels of latitude is 0 degrees. And it's measured in 90 degrees north or up to 90 degrees north and up to 90 degrees south of the equator. So you'll see it 90N and 90S. That's how you'll see it notated on like a chart or something like that, or GPS coordinates. You'll see 30 degrees north. Point A, we're going to talk about point A here in a little bit. So any questions on latitude and how it's measured? Okay, moving on. Longitude. So that's measured in degrees, minutes, and seconds, and it includes east or west. So the prime meridian is at 0 degrees longitude. And we'll talk about point A, like I said, here in a little bit. So that runs over through Greenwich, England, as you can see. right through England there and kind of through Africa. And it goes all the way the other side, the opposite side of the world is 180 degrees, so east or west. Excuse me. Yeah, so it keep in mind you can see that there's two 15 degrees there, so those would normally be notated east or west of the prime meridian. So here in North America, we are west, quite a ways west of the prime meridian. Most of us will be calling in from west of 100 degrees, on 100 degrees west of the prime meridian. So coordinates are given by grouping the latitude and longitude of a point together in that order. So we always do latitude first and then longitude. So a couple of examples. So 54 north, 110 west is Cold Lake, Alberta. 50 north and 115 west is Moose Jaw, and 50 north, 97 west is Winnipeg. So those are just kind of the general Latin law, and those are just in whole degrees. So we can further break that down. We can get a lot more accurate into degrees and then minutes and seconds in order to really kind of pinpoint depending on how accurate we need to be. So obviously, Winnipeg's a big city. So 50 north, 97 west might be, we're not sure if that's downtown. Is that out by the airport? Whereabouts is that, right? So we can, if we really need to, we can get really accurate with it. So any questions on how, if we were to notate latitude and longitude? Sometimes you might hear, you might hear 54 north, 110 west, or you might hear somebody say 54 north by 110 west, something like that, just to make sure we're talking about latitude and then longitude. But it's always done in that order. Latitude first and then longitude. For greater accuracy, each degree of latitude or longitude can be broken into 60 minutes, and each minute is broken down into 60 seconds. So that's exactly like time. Just remember, we're talking about, it's important that we're going to use units, right? So if we see 50 north, 25 minutes and 10 seconds, we have to make sure that we're talking about latitude or longitude, so geographical coordinates, or are we talking about time, right? So this instance, it's very broken down, very similar to time, so it makes it a little bit easier to kind of remember. So 60 seconds in a minute, 60 minutes in a degree. And you'll also see the quotation marks. So that's kind of like feet and inches for those of you who are familiar. So 1 degree, you have like the little circle, right? That notates degree, just like temperature does. And then you have the single kind of hash mark or quotation mark for minutes, and then the double hash mark or double quotation mark for seconds. So any questions on that at all? Perfect. Okay, so we're going to do a grid reference here. So who wants to take a crack at point A? So we're not going to get quite into point A is just like whole degrees here, so we'll start off easy. Who wants to take a crack at point A? Brito, go ahead.
1 degree north, 12 degrees east.
That's right, you got it. Yeah, right on. Here, take point B here. B is in Bravo. Who would like to take a crack at that? Hopefully we get some volunteers here. Otherwise, Nakashima, go ahead.
2 degrees south, 14 degrees east.
Bingo. Right on. So those are nice and easy because those are right on the line, right? So we've got, they're nice whole degrees. Now the next ones, C and D, you can see that they're a little bit offset, right? So we've got to kind of measure. Lots of times maps will have like little hash marks and stuff for us to kind of, do some interpretation. But for this one, we got to kind of, I don't know that we'll be able to get into seconds. You can get into it if you want. But Nakashima, did you have a question or you still have your hand up? Awesome. Who wants to take a crack at point C? See if we can get like maybe down to minutes. Brito, go ahead. You might still be muted there.
2 degrees and 5 minutes north, 14 degrees and 6 minutes east.
Sure, we can do that. So we know we have to do a little bit of interpretation here, right? So we know that it's north of 2 degrees, but it's not quite at 3. It's not really even halfway. it's not really even a third of the way. So it'd be even less than that, right? So we got to do a little bit of math in our head, right? So you did 5 minutes. Sure, I'd do something like that, 5 or 10 minutes, and then it'd be kind of close to the same going east longitude as well. So we know it's at least 14. It's not quite 15. And so we got to break it up into like 6, right? So we got to kind of draw a 6, I guess that's 0, and then this would be 6. So we got to draw like 5 imaginary hash marks in our head. And we would say, yeah, that'd be about 5 minutes in terms of longitude as well. So that's great. Yeah, good guess. So this one, obviously, it all depends on how precise we're trying to be, right? Like if we're just doing like ballpark Winnipeg, the city of Winnipeg is at, 50 north and whatever it was, 96 west. Sure, no problem. If we're trying to find a certain intersection, like where the IKEA is in Winnipeg, we might maybe need to be a little bit more precise, right? And those maps that are that zoomed in are going to have, some things to help you out. Awesome. Who would like to take a crack at point D, as in Delta? Anybody? I might start picking on people if I could. Thanks, Britt. I'll get you on the next one. Go ahead, Calder.
2 degrees south, 9 degrees and 30 minutes east.
Sure, yeah, I'd buy that. So we know it's 2 degrees south. It's right on the 2 line there for sure. And then it looks like it's about halfway between 9 and 10 degrees, right? So, which translates to 30 minutes. Remember, 1 degree is made up of 60 minutes, so that's about halfway. I'd buy that, absolutely. Yeah, great. Great job, everybody. So does anybody have any questions on this before we move on? This is just kind of a general overview. You'll get lots of practice when you actually go on course. You'll really get lots of practice on this. This one's a little bit harder to kind of do virtual means. If this is once you get into class, you're going to do lots of like tabletop exercises on trying to find all these grid references. Awesome, everybody. Okay, moving on. Great circles and rhumb lines. So there's 2 different things that we got to know about. So a great circle is a line that cuts the Earth perfectly in half and represents the shortest distance between 2 points. So an example of a great circle is the equator. So we know that the equator is a line that goes straight across the Earth, that cuts the Earth perfectly in half, and it's the shortest distance between 2 points. A rhumb line, conversely, a rhumb line is a line which cuts each meridian it crosses at the same angle. So a line which could be made by flying the same heading. So where this kind of gets complicated, if we were to fly the same heading, we're not going to fly straight across the Earth. It's going to make a big kind of almost zigzag pattern, really. It's like kind of, for those of you who have done, your FTX already, you do your compass march and you keep measuring, we keep trying to take our bearing, keep measuring, making sure we're following on the right track. If we were to do that over a long distance, it's going to start to, the line's going to look like it's actually curved instead of a straight line like a great circle is. As we keep cross-referencing our position in reference to the magnetic source. So we'll talk about that in a little bit. But one thing you need to know is a great circle is the shortest distance between 2 points, cuts the Earth perfectly in half, versus a rhumb line, it cuts each meridian it crosses at the same angle. Any questions about that? Perfect. Yeah, you'll definitely need to know those 2 definitions for sure. Great circle is like, you can think of it this way, like when we're trying to plan a flight, like I would like to fly from Calgary to Red Deer, going to meet a buddy, we're going to go out for a burger, and then I'm going to fly home. So when I draw a line between the Calgary airport and the Red Deer airport, if I draw a straight line, that is a great circle. All right, so that's like it's a straight line that we want to fly when we're flying. It's the most efficient, fuel efficient, shortest distance, etc. So true magnetic and calibrated headings. So it's a couple ways that we kind of reference. So true north and magnetic north are 2 different positions. You guys are mostly familiar with this already, but just remember they're measuring 2 different things. So true north is a point that is furthest north of the equator and aligns with the rotation of the Earth. So true north is in reference to the actual Earth. for the middle of it kind of is where rotation, and it never moves. So if you can think of it like true north is where Santa Claus lives, something like that, right? It never moves. It's always the same. The rotation of the Earth runs right through it. Versus magnetic north, that's where your compass points, right? So that's based on the Earth's magnetic fields, and it moves all the time. So it says it moves yearly, so it's adjusted yearly, but it's moving all the time because of magnetic material in the Earth's core, the Earth's spinning, so that gets kind of sloshed around. So magnetic north is always changing. So back like almost 200 years ago, it was like in the middle of the Canadian Arctic. And now it's like way in the middle of the Arctic Ocean somewhere, kind of approaching Russia, right? So magnetic north is all the time, or is moving all the time. So important to keep in mind that they're not the same location, and you'll need to know the difference between true north and magnetic north. Easiest way to remember it, magnetic north, so your compass measures magnetic field, right? So magnetic north relates to your compass, and it moves all the time. True north, it always stays the same. So most of the time, true north is what our maps are based on. Any questions on true north and magnetic north? Okay, moving on. So because of that, there's a couple of different adjustments that we have to make. So again, if we're tracking using true north, we're using a true heading. If you're tracking using magnetic north, you're on a magnetic heading. And because the aircraft is made of metal, there's spinning bits of metal like propellers. There's electronics as well. Certainly interfere with magnetism and measuring it. Compasses within an aircraft might not read accurately. So if you're to compensate for the error caused by the magnetic interference, you're flying a calibrated heading. So your compass in your airplane has to be, they call it a compass swing. So the mechanics have to go out and line it up with magnetic north and then kind of cancel out some errors, or if there is some errors, they have to note it down on a compass card, they call it. So pilots know how to correct that. Is there any questions on that? So there's certain corrections we have to make. So true magnetic and calibrated heading. So maps are often, they're laid out in true north. But our compass and our navigation is all done in magnetic. So we need a method to convert between the two. So in order to do that, we need to find the variation between the two. So it's just measuring the angular distance between true north and magnetic north, depending on where you're standing. In this example, you would need to add 30 degrees of variation to your magnetic heading to get the true heading. So you can see, think of it this way. So our maps are measured in true north, right? So we draw a line between us and Banff, and it says our heading that we need is 285 degrees, right? So our maps, because they're based on true, that says 285 degrees. However, what our compass reads is very different, right? Because those aren't based on true north, those are based on magnetic north. So it looks like there's a difference between about 30 degrees. So that's a little bit exaggerated just for the purposes of this lesson, but there's a big variation in between those two angles. Does that make sense? That's why it's called magnetic variation. Now, if we were to move, so this is like we're kind of looking at things, from the, southeast, right? If we were to move, now looks like I'm coming from, I don't know, Saskatoon. So in order to get from Saskatoon to Banff, our true heading is now like 225, right? But our magnetic heading, in order to make corrections so our compass gets us there, is only 15 degrees. The difference is only 15 degrees. And those are using the same point, right? So it all depends on where you're standing, the difference between the two. Brito, you have a question.
How do we determine variation?
That's a great question. We're going to get into that. So because our maps are based in true, but we navigate using magnetic, there's some lines on the map that are going to help us out with that. So this is just kind of the theory here right now, just the difference between true and magnetic. So we're using the same points, but depending on where we're coming from, it might be different. So it's just measuring the angle between the two. So any question on why, like what the difference is between the two? Here, I will get into another example for those of you who like the practical examples a little bit better, and that'll help us out. Okay, so the Earth is round. It's possible for many points to share the same magnetic variation, and these are called isogonic lines. On aviation charts, you find the variation by looking for the isogonic lines. And during a long flight, it's possible to pass multiple isogonic lines requiring small adjustments as you fly. So if it doesn't cross any lines, it can assume that the variation will remain constant the entire flight. So you need to know the definition of an isogonic line, which is line joining the same amount of magnetic variation. Interestingly, there's also something called an agonic line, A meaning the absence of or without. So there's line on that's actually kind of in between Winnipeg and Thunder Bay somewhere where there's 0 degrees of variation, right? So that's called an agonic line. And it'll be laid out just the exact same as this. So this is, you can see Lynn Lake, which is in northern Manitoba, right close to the Saskatchewan border. So the variation is about 6 degrees or 5 degrees, right? So we'll zoom in on it and I'll show you. So it's zoomed in, you can see that it's a little blurry there, but that purple dashed line that runs north to south through there where it says 6 degrees east. Same thing, here's another example over there where it says 5 degrees east. So that's a line of variation, a line joining the same area of variation, which is called an isogonic line. So definition of an isogonic line is a line joining a place of equal magnetic variation. So this is how we're going to compensate for the difference between true and magnetic. So this map would be, it's kind of pictured based on true north, but if we're using it for navigation, we've got to correct so that our compass reads properly. So if the flight path doesn't cross any lines, it can be assumed that the variation will remain constant the entire flight. So this is taken from an aviation map. So you can see, again, the picture's a little bit blurry there, but we can see there's obviously lots of water, right? Lots of lakes up in that part of the world. So if we were to fly east or west across this map, or east to west, sorry, across this map, you could see that we would fly over a couple of isogonic lines, right? A couple of lines of magnetic variation. So we'd have to make some adjustments. Any questions on that and what to find? So that's what we're looking for there is those dashed lines. So the other dash line, like, you know how it makes a grid with big and small hash marks that go kind of right through the middle. Though our aviation charts are covered in those, and those help us determine latitude and longitude right down to the nearest minute, and you can even interpret into seconds if you need to. Any questions on that? Perfect. All right, moving on. So isogonic meaning line of the same, joining the same magnetic variation. Agonic line meaning a line, a line joining places of no magnetic variation. So the difference between true north and magnetic north is 0. Okay, so compasses can be affected by interference. So again, because compasses measure the magnetic field of the Earth, they can be interfered with by things that create magnets. So giant metal spinny bits, such as our propeller, electronics, radios, things like that. Those all can interfere with our compass. So this is called deviation. So remember but there's magnetic variation, which is the difference between true and magnetic. And now from magnetic, to read it properly with our compass, we have to account for something called deviation, which is like things that interfere with our compass reading properly. So this is measured in degrees, just the same as latitude and longitude. So if we add or subtract the deviation, we get our calibrated heading. So magnetic heading is 360 declination. You'll see declination, you know, so if you remember from your FTX that the officers generally set the declination on the compass and they tell you not to mess with it. So that's what the declination is. Deviation's measured in degrees. If we add or subtract the deviation, we get our calibrated heading. So we'll go through a couple of examples. So deviation is to correct for compass error and compass interference. So we have a method for going through this so we can read it properly, going from our map to the airplane. Pilots will have to convert between headings. So an easy mnemonic to remember is TV makes dumb cadets, or TVMDC. So it goes, we start off with true, like if we start off with our map, we measure our line, we get our true track or true heading. Then we go to variation. So we are either add or subtract the magnetic variation to get from true to magnetic. And then in order to go from magnetic to make sure our compass reads properly, we have to add or subtract the deviation, right? So the way, remember that is TVM DC, or TV makes dumb cadets. So something to keep in mind. And there's a way that you have to know whether we add or subtract or variation and deviation. We'll talk about that in just a second. But you have to know how to get from true, which is our map, to magnetic all the way to compass, so that we can remember, so that we can navigate properly. So any questions on that? We'll go through an example here, a couple of examples here, I'll explain it a little bit more in depth. Okay. So variation and deviation will be provided in degrees either east or west. So for example, on this trip that you'll see, though, you'll be crossing one isogonic line labeled 5 degrees east. So remember on our map, we saw by Lynn Lake, there was that purple dashed line that had 5 degrees east on it. So that's our isogonic line of variation, 5 degrees east. This means that magnetic north is 5 degrees more than east than true north. So if you check your aircraft and you see there's a deviation of 2 degrees west when on a heading of 180, this means that you're flying 182 indicated. So helpful trick to remember whether we need to add or subtract is east is least and west is best. So we saw our isogonic line labeled 5 degrees east. That means we have to subtract 5 degrees from our true track to get to our magnetic track. So we'll go through it a little bit more on this slide. So remember, east is least, west is best. As long as we're following TVMDC, remember we we subtract east and we add west, as long as we're going left to right. So this is where the read the question, RTQ squared comes in. So as long as we're going left to right on this, going from true to magnetic to compass, east is least, west is best. If for whatever reason they ask us a question to go backwards, then we have to make sure that we got it right? So we might have to reverse the addition or subtraction, depending on what we're looking for, the answer we're trying to get. So make sure we read the question carefully. So we see our isogonic line that says 5 degrees east. We know east is least, west is best. In order to get from true to magnetic, we have to subtract 5 degrees. And that's the same thing for deviation as well. So the compass card tells us that we need a deviation of 2 degrees west. So that means we have to add 2 degrees. Convert a true heading to magnetic heading. Pilots apply the magnetic variation, also called declination. So again, declination, that's when we're out doing our FTX and we're trying to set our compass to get from the mess hall out to the first checkpoint in the middle of the bush somewhere. Declination is used for that. In the aviation context, we don't really call it declination. We call it magnetic variation. So any questions on that? This is the angular difference between true north and magnetic north, which varies by location. So example, when you're preparing your flight, the map, you want to head directly east at 90 degrees. So you cross one isogonic line with a variation of 5 degrees west. So we know east is least, west is best. So therefore, your magnetic heading will be 90 degrees plus 5 degrees equals 95 degrees. So we actually need to fly 95 degrees different. So that's the difference between true north and magnetic north. So we want to head directly, our true track or true heading is 90 degrees. But for magnetic wise, for our compass, it's 95 degrees. Any questions on east is least, west is best? So just remember our TVMDC, right? So this is the first kind of step of it, but to go between true and magnetic. And this is the same whether we're measuring true track, which is our line over the ground, or true heading, which is what direction our airplane is pointed. So remember, they're not always the same. Wind in particular tends to affect that. Any questions at all? Okay, moving on. Convert a true heading to magnetic heading. We apply the magnetic variation, which we just talked about. So an example, when preparing your flight that you want to head directly east at 90 degrees, you cross one isogonic line with a variation of 7 degrees east. So therefore, your magnetic heading will be 90 degrees minus 7 equals 0.83 degrees. Remember, east is least, west is best. We decided to subtract True being what our map is aligned with. Magnetic meaning this is how we're going to kind of measure it with our equipment, etc. So now this is the second step. So the last two examples, we're going from true to magnetic. Now we're going from magnetic to calibrated. So again, we're accounting for the errors of like interference on our compass in the airplane. To convert a magnetic heading to calibrated heading, pilots must correct for deviation. So when preparing your flight, you want to head directly south at 180 degrees. The little compass card in the airplane says that there's a 3 degrees westerly error on south heading. So therefore, your calibrated heading will be 180 plus 3 equals 183 degrees. So if we want to fly properly with our compass, we actually want to head south, but our compass, we have to make sure it points to 183 degrees. Any questions on that? East is least, west is best. Beautiful. Okay, moving on. Brito, go ahead.
How do we determine the deviation on the compass?
So it's in the airplane. There'll be a little card that the mechanics fill out after they evaluate the compass. They call it a compass swing. So they'll point the airplane directly south, and there's like it's a little compass rose on the ground actually. So they line everything up, make sure it's pointed directly south, and then they see what the compass is pointing at, so that they're able to measure it, and they'll write it out on a little compass card. So the compass card will say 4 south or 4 180 degrees. Steer 183, something like that. So it's aircraft dependent. So each individual, like we have a fleet of whatever it is, 25 gliders in Northwest region. Each glider will have a different deviation. Does that make sense? Good question.
That makes sense. Thank you.
Yeah, you bet. So whereas like variation, that's like laid out on a map, right? It's the same, depending, no matter, if you're to get a different map and look at it, it should still be the same as long as it's, made from the same year kind of thing. But deviation is each individual airplane will have its own kind of errors on it. So converting between headings. So putting it all together, you can attempt to answer the following question. We're flying from Mountain View to Saint Jean using a protractor on a map. So it's called a Douglas protractor. It's not like a protractor you might use in school. It's like a semicircle. A Douglas protractor is actually a square, and it's used to measure the angle for latitude and longitude, but also for measuring our track. So you determine your true heading that you need to fly of 262 degrees. First isogonic line you pass leaving Saint Jean indicates 13 degrees west. The bird dog, the tow plane that you're flying, has a compass card that says at 270 there's a 4 degrees easterly error. So what compass heading should we fly? So this, because we're flying, it says, even though it says 270 there's a 4 degree east, we're flying 262. So it's pretty close, right? We're flying in a westerly direction. So we have to go through the steps here. So true, we're starting out at 262, so you'd fill in the box true 262, and our variation indicates 13 degrees west. So Nakashima, go ahead.
I have an answer, but should I wait for everyone else to have an opportunity to finish?
Sure, just give us 10 seconds, if you to call on us here. Yeah, you bet. I'll call on you here in just a second.
Yes, sir.
So 262, and then remember east is least, west is best, so a variation in order to get to magnetic. And then our deviation, it says 4 degrees east to get from magnetic to compass. Awesome. Okay, go ahead, Nakashima.
Correct me if I'm wrong, 271 degrees.
Sure, so let's check our work. So we know that 262, and then our variation is 13 degrees west, so east is least, west is best, so we get to 275. So 262 plus 13 is 275. And then it says there's 4 degrees east of compass error for deviation, so magnetic to calibrated. So we were at 275, and then we got to subtract 4, gets us to 271. So what was your answer there, Nakashima? I can't remember.
Yeah, it was 271.
271. Awesome. Does everybody agree? Anybody have any questions on that? Math checks out. Okay, excellent. Does everybody understand this? We'll move on. We'll keep going. I think there might be one more example here. Okay, so this formula can be used algebraically to find missing information. So if they tell you have a magnetic heading of 165, but a true heading of 171, what's your variation? Is it east or west, right? So it looks like our magnetic heading, our true heading was 171. And then we have less, so 165 for magnetic versus true of 171. Brito, go ahead.
6 degrees east.
I'd agree. So remember, east is least, so we got to subtract if we want a less. So our true is 171. If we subtract 6, we get to 165. So yeah, that checks out for me as well. So that, I'm not sure if that'll come up on your exam to use this algebraically, but remember, you can go either direction, right? If you remember, we can go from magnetic to true, or we can start at true and go to magnetic. But just remember, if we go in order, TVMDC, that east is least, west is best. If you go backwards, then that's flipped, right? So it really helps when you see these navigation problems show up that you write down TVMDC, and so you can logically follow the steps. At least that helps me. If I try and do it in my head, you're bound to make an addition or subtraction error, or maybe go backwards instead, adding instead of subtracting, something like that. So it really helps to write this out. But TVMDC is a super helpful mnemonic. So there's a difference between bearing and heading. So bearing is the direction from one point to another, typically expressed in degrees from true or magnetic north. Refers to the direction of an object such as an airport or a navigational aid is from the aircraft. So I'm in my plane. I am over top of the IKEA in Winnipeg, and I'm going to the stadium, going to Princess Auto Stadium down by the university. So that bearing is 125 degrees from me to somewhere else. That bearing, over the ground is 125 degrees. Heading is the direction in which the aircraft's nose is pointing at any given time. So due to wind or other factors, the heading may not always align with the aircraft's track or the intended bearing. The aircraft's track almost never aligns with the intended bearing. So it's for those of you who are sailors or who have watched sailing, it's very similar to a sailboat that you have to turn into wind a little bit in order to fly, or in order to sail the direction you actually want to cover over the water. Same thing with airplanes. We have to turn into the wind a little bit in order to track the direction that we actually want to go. Wind's going to blow us off course, right? We're not glued to the road or anything like that, like a car is. So lots of these corrections that we have to make, we measure our track, right? We measure the line on the map, and then we have to apply the wind to see which direction we have to turn into the wind in order to keep going that direction. Does that make sense? You'll get into that again a little bit more once you go on course. You'll have a lot of these tabletop exercises to correct between your track and your wind. And then once we figure out our heading that we need to fly, then we have to apply the variation and deviation, right? So difference between bearing, which is the distance from me or to something on the ground, and heading is the direction that we're actually pointed. So heading is what our aircraft equipment is going to show as well. Our compass is going to show what direction we're pointed. It's not necessarily showing which direction we're going. Okay, so here's a graphical depiction, I guess. So our heading, the airplane's pointed obviously straight across the screen, but the wind you can see is coming from the north, so it's moving from the north to the south. So it's going to push us towards the bottom of the page. So for those of you that have done kinematics in school, measuring the distance, so it's all just triangles, right? We can measure this. This is measurable. This is activities that you're going to get to do. So it's going to push us to the south, even though the airplane's pointed straight across the screen. It's not actually going to travel that way because it's influenced by the wind. So 1 in 60 rule, this is just kind of a helpful thing when we're using our maps. So it's a simple rule of thumb used by pilots to estimate track correction when navigating. So the 1 in 60 rule goes, if the aircraft is 1 degree off its intended track over 60 miles, it will be 1 nautical mile off course. So this rule helps pilots calculate how much correction is needed if they deviate from their planned course. So remember, typically in navigation, we generally do it to nautical miles. So we got to make sure we use the right scale. This rule will apply even if you use statute miles as a unit instead of nautical miles. But just remember, just to make sure that we make sure we read our units. You know, if this comes up as a exercise during a tabletop or something like that, we've got to make sure we got our units first. So everything's in nautical miles or everything's in statute miles. But the example we often use is nautical miles because that's what we use in aviation most of the time. So if an aircraft is 1 degree off its intended track over 60 nautical miles, it will be 1 nautical mile off course. So this rule helps pilots calculate how much correction is needed if they deviate from our planned course. So we'll go through a couple of examples. So you can see 1 in 60, meaning 1 degree, 1 mile, and over the span of 60 miles. So it just makes a triangle is all it really does. Describing a triangle using round numbers. That's why it's the 1 in 60 rule. If it was less than that or not a round number, it would be, you know, you'd have a bunch of decimals and things like that, right? But we can interpolate this and extrapolate this to help ourselves out. So the 1 in 60 rule. Now, if we can do a little bit of algebra here. So it's describing a triangle using round numbers. You can adapt it. For example, after flying 120 miles, the pilot finds that they are 2 miles off course. So it looks like things just kind of doubled, didn't it? Right? So it was the 1 in 60 mile, but if we find that we've traveled 120 miles and now we're 2 miles off course, it's still approximately 1 degree off track, right? So it looks like it's just kind of the double the length. So each other number doubled. Now, try this again. 120 miles out and we forgot to calibrate our compass by 2 degrees. How far off course are we currently? So we're going to have to do some interpolation, a little bit of algebra, bit of equivalent multiplication. So it looks like it's 4 miles, right? So again, over 120 miles, we were 2 miles off course. So now if it's 2 degrees, it's actually going to be 4 miles, right? Short leg on a flight, and after 30 miles, we're 2 miles beside the bridge we were supposed to fly over. So what's our error? So this is half the distance, but it's double the error that we're kind of used to seeing, right? So there's a couple different ways that we can go about this, right? So if I were to, you know, extrapolate this to over 60 miles to make it, you know, the 1 in 60 rule. So it'd be 60 mile, probably be 4 miles off course. So it'll be 4 degrees. What else? Did anybody else get a different answer? How many degrees were we off by? What this is useful for is effects of wind and also potentially, you know, some sort of equipment error in our plane. But we planned to fly right over top of the bridge in downtown Calgary, and we're 2 miles off. You know, this is the heading that we were planned to fly, but we're 2 miles off. And so we say, hey, wait a second. You know, I need to adjust my course by 4 degrees because the wind pushed me 2 miles off further than I was planning to be. So it looks like I need to turn into the wind by a couple of miles or a couple of degrees, a couple more degrees in order to correct for that. The wind is a little bit stronger than was forecast. Does it make sense? That's what this is really helpful for. It tells us our error, yes, but it also helps us find a correction. Nakashima, go ahead.
So to be clear, every degree of variation after 60 nautical miles is 1 nautical mile variation.
No, this isn't describing TVMDC.
Or yeah,
So that
like sorry, like I mean error off the track.
It wouldn't necessarily be variation because we already measured that before we left, right? So the TVMDC is something we typically do before we depart, as long as we're on our planned flight. This would be for like correcting for the effects of wind, or if it was really bad, some sort of like equipment error or something like that.
Yeah.
So this has nothing to do with variation or anything like that. This is just how many miles we're off track.
Sorry, that's what I meant. That's what I meant. How many miles off track? So every degree after 60 nautical miles is a mile of difference off track.
Good question. Let's see. So it all kind of depends on the scale you're using, right? So if you were to double it to 120 miles, then that would make sense. But if you were trying to do after like 95 miles, you're going to have to do a little bit of algebra, right? Like
Yes.
a little bit of cross multiplication to try and figure that out.
Yes, sir.
So it helps if you use in like 60 or 30 or 120. So those are kind of simple factors to use. You can do it by a factor of like 93 miles if you want to, right? You're just going to get which is fine. As the pilot in command, you're responsible for going where you said you were going to go. So if you want to do that, absolutely. You can figure out, how many degrees we are off by, and then apply that. So good question. All right. So we got that sorted. So 1 in 60 rule. So now we're moving on to map projections. So is there any questions on the 1 in 60 rule? Awesome. So again, 1 in 60 rule, just for the definition. So you have it. Move back. So if an aircraft is 1 degree off its intended track over 60 nautical miles, it will be 1 nautical mile off course. So it helps us calculate how much correction is needed. So 1 degree of error over the span of 60 miles will result in you being off target by 1 mile. And again, that helps you find how many degrees you are off course. But remember, you got to make sure you're correct in whether you add your correction or subtract your correction from what you're currently doing, right? Depending on if you're left or right and we're heading east or west. Okay, so moving on to map projections now. So often referred to as a chart. Chart is it's the same thing as a map. They're often used interchangeably. Charts are just like aviation charts have like, that we've got other stuff on it besides just, Winnipeg and a bunch of highways, right? So you need to know these 4 things, basic elements of map construction. So there's 4 things: area, shapes, bearings, and distances. This is so tragically basic that I forget it almost every time, but they're almost guaranteed, depending on how long you decide to pursue aviation for. This question's going to come up, list the 4 basic elements of map construction, and you're like, oh, well, we've got like all kinds of colors, we got cities, we have highways, we got lakes, we got all sorts we got a million different things, but we're looking for like the 4 general big picture answers, and I forget it almost every time because it's like, why? It almost seems like a pointless question, but you need to know it. So there's areas, shapes, bearings, and distances. Those are the 4 basic elements of map construction. Normally, one of the elements is closely preserved and the others become distorted for reasons we'll talk about here in just a second. So again, 4 basic elements of map construction: areas, shapes, bearings, and distances. That'll come up on an exam almost guaranteed. So one of them is closely preserved, the others become distorted. So for aviation purposes, typically we want like a straight line to be a great circle. So it has to distort other things. So chart projections are the mathematical basis on which the maps are constructed. So they're a method to translate a 3D sphere onto a 2D page. So I'm not sure if some of you guys have had a chance to do this maybe while you're at cadets or maybe in school. But basically, there's a few different ways to skin the cat on how we get the Earth as we know is round. How do we get the information from a round globe onto a flat piece of paper so we can look at it? There's a few different ways. So we can use a cylinder, we can use a conic. So the conic is like, you can imagine it like there's a flashlight up at the top and it's shone over the globe. And then there's an azimuthal where they took like a straight line, they kind of took a slice off the Earth. And a cylinder is like they wrap like a piece of paper around it, and then draw what they need to and then unfold it. So there's always going to be errors when we take what's represented on a round surface and try and put it on a flat piece of paper. So if you've got a chance to do this exercise where like you draw like the continent of North America, if you have any of those mandarin oranges left over from Christmas, It really works well with those. So if you draw like a couple of different shapes on around orange while it's still, on the orange, and then you peel the orange and try and flatten out your orange peel with those shapes on it. Now that circle that you drew is going to be all distorted and wavy. It's not going to be round anymore, right? Same thing if you were to draw North America, it looks fine, based on what you drew when it was still on the orange. Once you peel it and try and flatten it out, it's going to maybe tear a little bit. What you thought was a straight line between 2 points is going to be curved. So that's why, for instance, when you look at a map, the classic one is, why does Greenland always look like it's the side? You can see it on this map, right? On the far left one, on the cylindrical one. Greenland is like almost the size of Africa, and it's not. It's like the size of Saskatchewan, if that. It's not that big. But because of the errors when trying to represent a round surface onto a flat piece of paper, that's why we get what we get. So there's a different type of map projection. So cylindrical is the Mercator projection. So that's the one where it looks like Greenland is the size of its own continent when it's actually not that big. So straight line paths are rhumb lines. So if we were to draw a line between Winnipeg and Calgary, that's actually a rhumb line. So that's the same heading. So less distortions near the equator. So the closer you get to the equator, the more accurate the map is for size. The negatives, the further away you get from the equator, the more distorted it gets. That's why Greenland is huge. So inaccurate distance measurements over a long distance. So it becomes very inaccurate for navigation if you're trying to go any sort of distance at all. This is where, so we take like a piece of paper and wrap it around the Earth, where the place where it's touching the Earth is at the equator. And then we draw, so that's why the parallels of latitude actually get spaced further and further away. So they're accurate near the equator, but where the further the paper is from actually touching the Earth, the more inaccurate it gets. So these maps are pretty to look at. They're not so great for navigation over long distances. Maybe for short range, it's not so bad, but long distance, it's not great. So Mercator projection is cylindrical. So there's transverse cylindrical, which is transverse Mercator. So instead of that piece of paper touching the Earth at the equator, it's touching on maybe the prime meridian or something. So where do we have that? Okay, so transverse Mercator. It's accurate along central meridian, making it suitable for north-south flights, and it's ideal for narrow provinces like Manitoba or Nova Scotia. The distortion increases the further east or west you go, and it's not ideal for cross countries over multiple provinces. So it's great for north-south in kind of a small area. So, but not great if we're going like a long distance east to west. It's not great because it gets distorted the further away from the center you go. So this is used in a VFR terminal area chart. So remember VFR, visual flight rules, and a terminal area chart. So the VTAs, they're used for like really zoomed in on a particular location. So that gives us like particular procedures for an area. So for instance, Calgary has a VTA, and that's if we're flying VFR around the Calgary area, it's really zoomed in on Calgary and the surrounding area instead of like a big, half a province kind of thing. So that has like various checkpoints. It's got landmarks on it. It's got power lines. It's got all kinds of good stuff on it. So it's useful when we're flying close to busy airspace. But if we're trying to fly from Calgary to Winnipeg, it's not great. So conic projection. So the Lambert conformal conic projection is what we use. So this is like kind of shining a flashlight behind the Earth, and you can kind of see how it expands in a cone like a flashlight does. So it's the least distortion in mid-latitudes, such as the Canada and the United States. So mid-latitudes meaning, so remember the equator is 0 and the North Pole is 90. So for mid-latitudes and between that, it's great. Less distortion of shape and distance versus cylindrical projections. There's significant distortion near polar regions, and two standard parallels make a wavy kind of distortion pattern. So what's good about the Lambert conic conformal projection is that a straight line on these charts is a great circle. So if I draw a line between Winnipeg and Calgary, that is the shortest possible distance between those 2 points if we use this map, right? So in a Lambert conic conformal projection, a straight line is actually a great circle, shortest distance between 2 points, right? So this is used in VFR navigational charts, or VNCs. So this is a little bit bigger kind of picture. Remember, the VTA is like zoomed in on a particular city. VFR navigational chart covers like, half a province kind of thing. There's one for Edmonton and another one for Calgary that covers, it'll go from like northeastern BC to northwestern Saskatchewan kind of thing. So any questions on the Lambert conformal conic projection? So this is what we like to use if we're planning our cross country. You're going from Winnipeg to Prince Albert to meet one of your course mates for lunch, and then you're going to fly home. This is the map you're going to use. So polar chart, so azimuthal, or which is polar azimuthal. So this is ideal for polar flights. So remember how we talked about the meridians of longitude, that they converge on the poles? So that makes navigation kind of difficult because those angles are always changing, right? Everything's kind of converging. All those lines are coming together. All those isogonic lines of variation, they're all coming together. So it's really hard. Your equipment tends to get a little bit confused. So this projection helps kind of spread things out a little bit. Provides true directional bearing from the center point, and it distorts shape and size the further away you get from the center. It's only suitable for very localized areas. So this is like we're actually flying over the North Pole kind of thing. So this is used in polar charts. We won't have to worry too much about that, but that's an example of it. So this is where it's really kind of helpful for a localized area. So great circles and rhumb lines. So drawing a straight line on different projection will yield different results. So remember, we talked about the Lambert projection. So a straight line on the Lambert projection gives you a great circle route. A straight line on the Mercator projection gives you a rhumb line. So those two things we like to use for two different purposes. Any questions on that? You'll need to know that. Usually the easiest way to remember that is a straight line measured on the Lambert conformal conic projection is a great circle. And then after that, you can kind of fill in the blanks. That's how I remember that. But you'll need to know that a straight line measured on the Lambert conformal conic projection is a great circle, which is, of course, the shortest distance between 2 points. Okay, so we've talked about different projections and how now we're going to talk about what type of charts they're used on. So safe and accurate flight planning and execution. So these charts provide vital information for both visual and instrument navigation. So they include our VFR navigational charts. So visual flight rules navigational charts are VNCs. So those are what you're going to use for like a cross-country flight. They have our VFR terminal area charts. So VTAs, so those are like zoomed in. So terminal in this case, meaning like remember our airspace classification. So the control tower just kind of directs everything that's going on around the airport. The terminal area is everything like it's an expanded view kind of over top of the city, right? So terminal is usually what's happening not at the airport, but the airspace around the airport, usually around 30 miles. So the VTA will be expanded out to, maybe a little bit further than 30 miles for airspace. It'll be expanded out just outside of that so you can see what's going on. Our en route charts, which are low and high altitude. So those are like real long distance en route, low and high. So that's like we're flying from Vancouver to Moncton kind of thing. Those are like zoomed out even further. And then of course our Canadian Flight Supplement, our CFS that we covered in the first ground school lesson, I think. Might have been the second one before Christmas there. So these are different types of charts and things that we use. You guys will be confer with 3 out of 4. So you'll need to know kind of what an en route chart is. That's for like kind of cross continent type of thing. But you'll get very familiar once you go on course with VNCs, VTAs, and CFSs. So VNCs are used for visual flight rules navigation. These charts we get topographical details. So we got terrain, lakes, rivers, and also prominent man-made features. So we got cities, we've got highways, we've got towns. We have towns, they've got towns labeled on those VNCs that haven't existed for a long, long time. So it's careful with that because every little town that was a railway stop on the prairies is still listed on those VNCs. So if you're going to use something for a landmark, make sure it's something that you're familiar with or it's a big enough town. Terrain, lakes, rivers, prominent man-made features, as well as airspace boundaries, major airports, and navigational aids. So we can see if they give examples here. So let's see. So on our VNC, we have red circle, which is CFB Winnipeg or the city of Winnipeg. So you can see right at the bottom, that yellow blob there where it says Winnipeg is obviously the city of Winnipeg. Blue circle, that's St. Andrews. That's St. Andrews Airport. So that's a long time for those of you that are applying for power. Lots of years they have power in St. Andrews. And then the orange circle is where Cadet Flight Training Center Gimli used to be. So you can see we've got all kinds of highways in between. We have airspace, so this hash mark, let's see if I can get the laser. Here we go. So this hash mark right here that I'm highlighting in yellow, so that is airspace. You can see all the highways there in red. Where it says VTA here, so that's telling you that there's another chart, there's a VTA for that particular airspace, and if you want more information, you should have a look at the VTA instead of the VNC that we're looking at. We've got power lines. Let's see if I can find one here. There's all kinds of hydropower in Manitoba, so there's probably some power lines, and there's, here we go. So that squiggle line that's kind of moving up the right side. So those are power lines and also the towers that are on the power line. You've got that symbol right there over, looks like woodlands. So that looks like an ultralight flying area. Up here near Gimli, you've got a glider, all sorts of good stuff. And then of course, we've got a VOR right there, the Langrooth VOR. Okay, let's shut that off. Okay, so any questions on things that we can find on a VNC? So, and of course, this is just kind of one part of a VNC. This particular VNC will take you all the way to Regina, and then almost as far north as Flin Flon. So now we're on our VTA. There's a much higher level of detail, right? So it's zoomed in. So this VTA, like it said, was zoomed in on the city of Winnipeg. So Gimli is no longer visible. That's outside the bounds of this VTA. Unique landmarks such as IKEA. So you can see on the bottom portion that IKEA that's got a little flag on it. So that's like a checkpoint. When you're flying around, they'll tell you to maybe head towards the IKEA at 4,500. So that's where you know where to find it. St. Andrews also has prescribed entry and exit paths here. So let me find my highlighter again. So you can see those arrows that look like they kind of sort of follow the highway to and from Winnipeg. So those are VFR corridors. So if you're heading from St. Andrews into Winnipeg, we're on the west side of the highway. And if we're heading back to St. Andrews from the city, then we're on the east side of the highway. We've also got airspace. So those they're sort of horseshoe shaped, I guess. That circle that's around the Winnipeg International Airport. So that's the tower's boundary. So that's where instead of talking to terminal or somebody else, we should be talking to the tower. We've also got the Winnipeg NDB here. So non-directional beacon. We'll get into that in radio aids. We can see here that we've got the airspace designation. So who we should be talking to at what altitude. We've got the floodway bridge, another call-up point. We've got some CYR, so we've got restricted airspace. So again, this is really helpful for when we're flying into, so for those of you who aren't from Winnipeg and don't have one of these, after you go on power and you're trying to visit your buddy in St. Andrews, you should probably buy a Winnipeg VTA before you go. So it's got some helpful information. Okay, so they're focused on busy terminal areas around major airports, providing detailed information on controlled airspace and traffic zones, offer a higher detail, and are designed to aid in navigation in complex congested airspace close to terminal. So we're out of like I'm just, cruising between Winnipeg and Calgary. We're just out now, we're like, we're getting close to Winnipeg, and there's some specific procedures for that particular airspace. So that's where we find these, is on these VTAs. VNCs are scaled at 1 to 500,000. So you might need to know this. So the VNC, the scale is 1 to 500,000, are suitable for en route navigation at lower altitudes. So that, remember, that's a ratio or a scale. So 1 inch is equal to 500,000 inches, or, if you were to measure like 1 foot, for whatever reason you're using that on that chart, is equal to 500,000 feet in real life. So the best, usually the way that we do that is we have a ruler that has little hash marks on it. So it has that scale for us. But you need to know that that ratio or that scale is 1 inch on the map equals 500,000 units in real life. So 1 to 500,000 on the VNC. VTAs are scaled at 1 to 250,000, which is congested localized airspace. Nav Canada offers 52 VNC maps, and it offers 7 VTAs. So let's see if I can figure out where the zoom button is. There. So this is our VNC. So you can see all the different VNCs that they have available to us. So we've got Winnipeg, which is kind of bottom in the center. There's Regina, Flin Flon, Edmonton, Calgary, Prince George, Vancouver. Kitimat, I think, is the one out on the west coast. So those are the different VNCs that we have available to us. And then it's got all kinds, it's got a legend on it. Same with our VTA. It's got a legend right on it. Lots of times the exams will ask you questions about what does this mean on the map. If you look at the front of the map, it usually tells you the answer. So different scales. VNCs are 1 to 500,000 because they're bigger, and VTAs are 1 to 250,000. And we have our en route charts. So they're used for IFR navigation. They depict airways, waypoints, navigation aids such as VORs and NDBs, minimum en route altitudes. So low altitude en route charts are used below 24,000 feet, while high altitude charts cover airways at higher altitudes, and they're typically used for longer flights. And often they don't have as much detail. So you're not going to see like the IKEA in Winnipeg on these charts, right? They're used for IFR when we can't see the ground. Any questions on en route charts? And then we have our CFS. So it's an essential publication for all pilots, so you have to have it, really. Contains detailed information about every registered airport, heliport, and aerodrome. It includes runway details, so how long it is, how wide they are, communication frequencies, services, procedure for entering and leaving controlled airspace. They got phone numbers for fixed base operators, like how do we get gas at this airport? Where do I find customs? Things like that. It's got all that information in there. So it's updated every 56 days and is a critical tool for every pilot in Canada. Okay, so I'm going to go through a quick review. Whoops. Describe longitude and latitude. Somebody describe longitude and latitude for me. I'll probably just go down the list and start calling on everybody. Calder, can you describe longitude and latitude for me? Calder, if you're trying to talk, you'd be muted there. Okay, I'll move down the list. Nakashima, can you describe longitude and latitude?
Yeah, so longitude, so latitude runs from east to west. They're numbered
Right.
90 degrees from north. They run north to south from the equator. And then
Right.
meridian to longitude run from north to south. They're numbered 0 to 180 degrees. They run from east to west, and they converge on the poles.
Absolutely. Yeah. So just remember that they're labeled from either 0 to 90 for latitude and 0 to 180 for longitude. Just remember that also includes east or west, right? So it'll be like 90 degrees north or 90 degrees south, and same thing for longitude. So it'll be 30 degrees east or 30 degrees west. Good. Great. Grid coordinates. So we kind of talked about that. We did that exercise already. Difference between a rum line and a great circle. Newkirk, if you're there, can you tell me, you can take a crack at one or both of those if you want.
The Great Circle is the shortest point between 2 points on a spear, and the
Right, yeah.
run line is a path with a constant bearing.
Constant heading. Yeah, you got it. Absolutely. Or constant bearing. You're right. Yeah, it cuts the meridian at the same angle as you go along. So it'll kind of make a bit of a zigzag pattern. Awesome. Great. We did the exercise between true magnetic and calibrated headings already. We did the conversion. Difference between bearing and heading. Let's see. Bird, can you tell me the difference between what your bearing is and what your heading is? Bird, if you're there trying to talk, you might have the mute on there. You can take a crack at one or both if you'd like, or put it in the chat. Okay, I'm not sure if Bird is there. So let's talk to Zografros. Zografros. Pardon me, I'm sorry. Let me know how to pronounce that properly. Zografos, if you're there. Can you take a crack at heading or bearing? Yeah, sure, go ahead. What's bearing? Okay, while he types out an answer for bearing, does somebody want to take a crack at heading? Yeah, so bearing the angle measuring the observer to an object, that's great. So what's the direction from me to the IKEA in Winnipeg? That's the bearing, right? Okay, Brito, you had your hand up there. You can tackle heading there if you want.
The direction the nose of the plane is pointing?
Yeah, the direction you're pointing. Yeah, that's really all it is. It measures, is what your heading is. Awesome. Do you want to take a crack at the 1 in 60 rule as well?
If you travel 60 miles with a variation of 1 degree, then you'll be off by 1 mile after those 60 miles.
You bet. So not variation. So want to keep that clear. Just remember, variation that's the difference between true north and magnetic north. So this is like if you're 1 degree in error. So if we travel 60 miles and we're 1 degree off on our, like we're 1 degree in error from where we said we were going to be traveling, we'll be 1 mile off over the span of 6. So variation doesn't have anything to do with that particular one. So just make sure we keep variation separate for when we're doing TBMDC. But otherwise, yeah, great answer. So just remember if we're 1 degree in error is what it is. So it's not 1 degree in variation. Awesome. And we talked about map projections and navigational aids. Okay. So are there any questions about that? All right. So it looks like we did pretty well with that. That's a long one. All right, everybody, welcome back. Okay. Get to a second just to come back here. Now, did anybody take a look at any of the METARs and wanted to take a crack at one of them? Calder, go ahead.
I'll do the Calgary one.
Calgary, yeah, go ahead.
The METAR at Calgary was published the 23rd of the month at midnight Zulu. Winds are 290 at 2 knots. Visibility 40 statute miles. Few clouds at 25,000 feet. Temperature is 0, dew point -11. Altimeter 30.45. Cirrus 2 octas and sea level pressure 300.
Awesome.
Yeah.
You bet. So yeah, that's great. So for Calgary, what the wind, when you said the wind, is that true or magnetic? Remember? Okay, if you don't. The way I remember it is always, the weatherman is always true. So in this case, it's telling us that it's 290 degrees true at 2 knots. So usually if you see it written down in aviation format anyways, if you see it written down, typically it's in degrees true. If you hear it like over the radio or something, so the tower tells you before you land or it's broadcast on the ATIS, then that's typically magnetic. So it's a little bit more relevant. But typically when you see it down, the weatherman's always true as I remember. Awesome. Anybody else want to take a crack at one of them? Okay, no volunteers. Well, thanks, Calder. Let's see. I've got for Saskatoon here. What is that I've highlighted there? What does that mean? Let's see if I can zoom in a little bit. So I've highlighted that. What does that mean? Does anybody know? Riddle?
Drifting snow.
Yeah, and yeah, so drifting snow, the second half of it's right. Yeah, you got it. Drifting snow. What's the first part?
Snow.
You remember?
Accumulation.
You bet. So SN is snow, right? Absolutely. What does the minus sign mean? Do you remember? With a dash.
I don't remember, sir.
What would plus mean? Does that help you out at all? That's okay if you don't. Not a big deal. Let's see. Newkirk.
The minus means light snow.
Light, you got it. Yeah, awesome job, everybody. So we got light snow and drifting snow in Saskatoon. Awesome. So if there was no minus here, if it just said SN like this, so that would be moderate snow. And then if it was plus SN, that would be heavy snow. Something to keep in mind. Awesome. Let's see. What about, we've got CYRT here, what I just highlighted. What does that mean? Actually, what does all three of those mean? Anybody want to take a crack at those? Nakashima?
Correct me if I'm wrong, but icing, blowing snow, and I can't quite remember.
No problem. You got BLSN is absolutely blowing snow. You got that for sure. Brito, go ahead.
SKC means scattered clouds.
In this instance, it doesn't. It actually means sky clear.
Oh, I thought that's what it was. I wasn't gonna say that though.
Yeah. So in this particular instance, SKC is sky clear. So if you wanted, let's see, it would. Do we have any of them with? Looks like we don't have any of them with scattered. So it would see SCT would be scattered. And that would be listed right after the visibility. So you can see few is 25,000, broken is 13,000. And then this particular instance, SKC means sky clear. So no clouds. IC, does anybody know what IC is? Newkirk?
Ice crystals.
Ice crystals, you got it. So CYRT is Rankin Inlet, Nunavut. So we got visibility is 6 miles in ice crystals, blowing snow, and it's sky clear. So it makes sense that there's blowing snow because the wind's 340 at 24 knots. So that's like, almost 35 kilometers an hour, just ballpark. It's quite windy there. But yeah, so we've got some blowing snow, but it's sky clear. Right. So your instructor probably told you when you guys did this. I know that class was pretty long when you guys got into METARs and TAFs. But what I would do is I would get into this almost every single day. Or I would do. So plan.navcanada.ca is something that you should have favorited. And then where it says welcome weather NOTAM and GFA. So you should click weather NOTAM. And then you want to enter some airports. So we don't want any of the AirMet, SIGMET, NOTAM. So just leave METAR and TAF checked for now. And if you want, you can do like the last 3 hours. Remember, they're measured every hour on the hour. So we want the last 3 hours, and then you can enter whatever airports you want. So, whoops, we can do Calgary, Winnipeg, Saskatoon, and then we had, no, I want CYRT. Rankin, Thompson, and see, just for fun, Iqaluit. Okay, so then it's going to give you all kinds of good stuff here. Yeah, we've got a couple of tricky ones there in Saskatoon, it looks like. Rankin Inlet, it's very cold. Thompson, it's cold, but not as bad as Rankin. Here we've got a couple of good, here's a juicy one in Iqaluit. Let's see if I can zoom in just a little bit for us here. So who wants to take a crack at that one? That's a tricky one. I might have to zoom out even more. There. So that's a tricky one right there. So does anybody remember, or we can, if you want, you can kind of put a piece of it into the chat, or if somebody wants to say out loud what they're seeing, they can, you can do it out loud too. But if anybody want to take a crack at that one, that's a juicy one. Give you a second to read it there. So again, while you're having a look, plan.navcanada.ca, make sure you click on weather and NOTAM, and then just have a look at these when you're on the bus to school, or on your way home, or on your way to or from somewhere. You guys should get real familiar with these. And then if you're you see something where you're like, what does that mean? I don't really know what that means. You can try and look it up. There's also the option for plain language as well, or ask an instructor too. I know we've only got a few weeks, like a week or two left of review there, but bring it up to your instructor and say, hey, I saw this, sir or ma'am, do you mind helping me out with this? I'm not sure what it means. Okay, so report for CYFB is Iqaluit, 23rd day at 02 Zulu. Winds 340 degrees true at 18 knots. Visibility, 1 statute mile. Okay, and then this. So runway 34, visibility is 5,500, varying to 6,000 feet, with the /D means downward trend. So that means it's showing the RVR from the runway visual range. So the RVR is varying between 5,500 and 6,000 feet with a downward trend. Then we have light snow. So -SN means light snow. Blowing snow, overcast at 2,500. Temperature of -15, dew point of -18. Altimeter is 2894, so that's a very low altimeter setting. 28.94 inches of mercury, and then RMK means remarks. So remarks, blowing snow 6, and SC, remember SC, if we think back to our clouds, so that's stratocumulus too. So 6 octaves of blowing snow and 2 octaves of stratocumulus. Visibility is variable between 3/4 of a mile and 1 1/4 mile, and then it's got the sea level pressure on there as well. So that's it's a blustery winter day there in Iqaluit. So that typically, if the altimeter ever goes below 2.9 something, it's a very low pressure. So it's not a great day for be outside there in Iqaluit. And then of course we got the TAFs there too. So awesome. Okay, enough on that. Good job, you guys. But yeah, I would heavily encourage you guys to get into those METAR and TAFs and GFAs if you learned how to do them. Okay, so we're gonna do this. Okay, using charts. So we talked about like the projections and all that. So now we're gonna get a little bit more in depth on how to use them. Once again, Lieutenant Shaw. So aeronautical charts have unique features that are not often found in other types of maps. So they're purpose built for aeronautics, right? So we have airspaces on them. We've got airport information. We've got radio aids, communication frequencies. We've got our lines of deviation. Remember our isogonic lines or our agonic line. Obstruction heights, hyposymmetric tints. That's a fancy word for different coloring for elevation. You'll see that it's not as visible on a Winnipeg one because it's obviously the elevation isn't that high and there's not a lot of mountains in the way. And then elevation depictions as well. So using aeronautical charts, so we've got, this is the front of the Regina VNC. So it folds up nice and neat. First part of the map legend includes a guide to read the following. So our aerodrome information, so symbols for aerodrome types, aerodrome data, and airspace markings. So as you can see on the front of it, it's got all kinds of juicy information on here, and we're just going to go through it. So our airport information, so our symbols for airport types. So we've got airports with services are kind of laid out like this. So they either have the runway layout or they've got kind of a circle with the runway layout on it. So only usable runways are shown and patterns are drawn at chart scale. So without hard surface runways, it just kind of looks like a bullseye sort of. And then if it's on the water, obviously we've got a little anchor on that to make it look like it's a water drone. Other airports, then we just have land, water, got a heliport, got a hospital with a heliport. It's a square instead of a circle. Abandoned, so not a good idea to use that. And then status unknown for that. So we got different symbols on there. So hard surface, so you'll see the runway layout at like major international airports. You'll see it kind of laid out like that. Otherwise, you'll just kind of see it almost looks like a do not enter sign, sort of. Okay, aerodrome data. So can see kind of the top left, we've got a little hash mark box around name. We've got a bunch of letters, numbers, days 60, or name M, a box with an L. I've got all kinds of funky stuff on there. And this breaks it down for us. So the dashed box means that there's customs available at that airport. ATIS means that it's got the automatic terminal information service. So that's like a frequency that you tune up that tells you what the airport, it'll give you the weather. It'll tell you what runway they're using for arrivals and what runway they're using for departures, things like that. Elevation in feet. So 371. So we can see this name airport has customs. It's at 371 feet above sea level. It's got L, so runway lighting. RCAL, so the box around the L, that's on the second example. So name M371L. So RCAL is radio controlled airport lighting. So what that is the lights are normally off if no one's there. You just have to key your microphone, depending on what type of RCAL it is. It's either 7 or 5 times. So you'll key your microphone, and then a couple seconds later, all the airport lights will come on. And then you key your microphone either 3, 5, or 7 times, depending on the brightness, how you want them. So it's airport aerodrome radio controlled lighting, approach lights. Limited hours or OR, so CCFS. So the star, if it's got a star next to it, it's only open limited hours. H for hard surface runway, and then 53 is the longest landing distance in hundreds of feet. So 53 indicates the length between 5270 and 5369. So you can see H53 means that it's a hard surface runway, and the longest one is about 5,300 feet long. And then we've got an interesting note for days 60. So that's our daytime landing distance. So sometimes in the daytime, it's 6,000 feet at this particular airport, whereas in the nighttime, it's only 5,300. AM means mandatory frequency. So on the middle example there, you can see where it says M122.3. So the mandatory frequency you got to be talking to people on is 122.3. A is aerodrome traffic frequency, so it's a little bit less strict. U is a private advisory, so it's Unicom. Common traffic advisory frequency, so some of the southern Canadian charts might have a US airport or two on it, so they call it something different in the US, a CTAF. And S is a sheltered mooring area, so place to tie down your airplane. M is military airport. Restricted, so PPR, you can see prior permission required is what PPR means. So you're not allowed to use it unless you have permission. Sometimes you might see PNR, which means prior notice required. So you're allowed to use it. You just have to tell them you're going to first. R is restricted, so it's PPR only by specific authorization. And then we've got the hollow star there, which is the airport beacon. And then no SVFR means no special VFR. Again, that's in the US. Next up, we've got airspace information. So we have all kinds of stuff. So controlled airspace below flight level 180 is shown. So that's important to know. Again, this is a lower from the surface to flight level 180. It doesn't really show anything above that. And then it says transponder mode C is required in all Class B and Class C airspace. Remember, Class C in Canada stands for C for controlled, so that's like a controlled airport. And then Class B is in Bravo is like from 12,500 up to flight level 180. And other places if it's donated. So we've got a controlled area boundary, we've got airway, we have air route. So there's a difference between airway and air route. Military training, we got VFR, compulsory reporting points, changeover points, airspace boundary where it's transponder mode C. We've got a boundary between controlled areas with different floors. So it's kind of the zigzaggy one. And then on the right side, we have the CZ stands for control zone. So it's a control zone to 3,000 feet, so 2,700 feet above the ground. Control zone is D is in Delta, so to 3,000. What else do we have? Class E, the box with the hash marks in it. So that's Class F airspace or special use airspace. So in Canada, we have CYA, CYD, and CYR. So CYA is advisory. So that'll be like if there's gliding going on there, for instance, that'll be CYA. D is in danger. So that's like if there's like blasting or something going on, like there's mining and blasting going on. So you got to be careful. And then CYR is restricted. So that's like the military or over top of a prison, something like that. And then area activity codes. So we have CYA 118. So CYA, remember, is advisory. 118 is the number. And then A, we can see here that there's acrobatics. So it looks like there's aerobatics going on inside that airspace. Flight tests, hang gliding, we got military, parachute, soaring, training. And then we've got a few different, so hang gliding, ultralight, things like that. So you guys have all been able to see that. But again, you're going to see the busier the airspace is, the more congested this is going to be. So Winnipeg is going to have, a bunch of pretty colors and a bunch of lines on it and things like that you got to pay attention to. If you go to Vancouver, there's going to be stuff everywhere, right? So if you see something that you're not sure, oftentimes the front of the map will have a definition. So always keep an eye out for your Class F or special use airspace. So this is the back of it. It's just got further, so it has things for about radio aids, air ground communication boxes, and then miscellaneous information. And then let's see, other map features like isogonic line, hazards, and MEF. I'm not sure. Oh, the spot heights. Radio aids to navigation. So this is a symbol for ground stations. Most of these things are used in IFR. Sometimes in VFR, you might have to navigate to something like that. So VOR stands for VHF omnidirectional range. So you can think about like spokes on a bicycle. It has, you can navigate to or from that particular station or in a certain direction by tuning up exactly what radial you want. It goes from 360 degrees. It's got a radial that kind of points in every direction, like I said, spokes on a bicycle tire or a bicycle wheel. So you can navigate in a certain direction or to or from somewhere using that. DME is distance measuring equipment, so that measures the time difference from the signal and tells you your distance. A VORTAC combines a VOR and a TACAN. A TACAN is for military. Those are in use at military airports, so VORTAC combines the two. NDB, non-directional beacon, so that's kind of different than a VOR. You tune it up in your equipment in the plane, and it says the beacon is over there. So it doesn't have like all the different radials like the spokes on a bicycle like a VOR does. It just says the equipment in your airplane will just point to it. Commercial broadcasting station, so that's like 92.9 or whatever. That's like a regular radio station. And then you can see there's a little dot. So you can see inside that runway layout, there's a little dot on the right-hand side of the intersection. So that indicates where the radio facility is. If it's too close to the runways, that'll tell you where it is. Radio aids to navigation boxes. So this is, look, it tells us that there's a VOR and a DME. It tells us there's a TACAN, and then the dots and dashes is Morse code. So if you tune it up and actually listen to it, you'll hear the dots and dashes. So that's how you have to identify and make sure that the station's working properly. Kamloops, and then Halifax, of course, where they combine the VHF and LF, low frequency. Don't have to worry too much about TACAN. Again, that's more of a military thing. A VORTAC combines a VOR and a TACAN, so you'll see that sometimes. TACAN and DME channels are without voice and not underlined. Private indicates that it's not run by NAV Canada. TWD, transcribed weather broadcast, no ATIS. Anyways, continuing on. So heavy boxes indicate FSS with standard group frequencies like 126.7. So 126.7 is en route. 121.5 you should probably know. 121.5 is the emergency frequency. So that's in VHF. If 243 is in UHF, so ultra high frequency. Typically, we're always in VHF. The only people that really use UHF is the military. Other frequencies are available. It shows, again, in the US, it tells you something different. OT means other times. So FSS, you can see in that second example, FSS operated limited hours, other times see CFS. So the CFS will tell you when it's closed. Thin line boxes, they're remote to site, so they're not actually on site with you, but you're still talking to somebody. And it'll tell you what frequency to use. So again, miscellaneous information. So the isogonic lines, we have the hazards and maximum elevation figures. So again, lines of equal magnetic variation, isogonic. If it said 0, that's an agonic line. We have transmission lines, so power lines. We got a cable span over top of the river, marine lights. Got obstructions, so sometimes those are like smokestacks or whatever. Elevation in feet, ASL, so that's sometimes called a spot height. So you can see it says 1749 or 1064, so it's known as spot height. Lighting annotation, so MEF, maximum elevation figure, shown in quadrangles by the ticked lines of latitude and longitude, thousands and hundreds of feet. So there's 3 and then the lowercase, or the smaller 8. So 3,800 is the maximum elevation figure in that particular quadrant. And that's based on known information, so they might not have it. So this tells you how to read your lines of latitude and longitude. And then we have the hyposymmetric tint, which again, you've seen this before. This is just a technical name. So the deeper the color gets, the higher the elevation is really. 6916 tells you the highest elevation in that particular map. And then we have Medicine Hat. So again, continuing on. So hyposymmetric layer, you can see the area around Wood Mountain is like a darker orange brown. So that just tells you that it's in higher elevation. As you can see, so the area around that is the MEF, the maximum elevation figure. It's 3,700 compared to if you go to like the top right up by wherever that is, Weyburn, it looks like it's like 2,700, right? So not a whole lot to see. And then, of course, our line of deviation, we can see it kind of running that purple dash line. You can see towards the bottom there, down by Glasgow, North Dakota, it says 12 degrees east. It's really hard to do, like virtually. Again, you'll be doing lots of kind of tabletop exercises once you actually go to summer camp. Remember we went through this last time, our scale, so you need to know the scale, 1 to 250,000 for the VTA, 1 to 500,000 for the VNC. Measuring distance on a map, so it's got the scale here for you. It's graduated scale. If you didn't have your own ruler, I guess you could make one with this. Example above is the graduated scale on the VNC. View the 0 at the arrow above. The right is primary scale, while to the left is the extension scale. We have a ruler that does that for us. So it's just IKO ruler. Ensure you're using the correct scale on the ruler, or you can draw this out on your own piece of paper. So correct scale means that you can see ICAO chart rule. The part that we can read, inner scale is 1 to 1 million, and the outer scale is 1 to 500,000. So we're interested in using the 1 to 500,000 scale because that's for VNCs, right? But you can see that's in statute miles. We don't want statute miles. We want nautical miles, right? So you can see the scale, it's upside down. So just make sure we're using the correct one, right? We want to make sure we're using nautical miles, if that's what your airplane is measured in, is using knots and nautical miles instead of statute miles. So it's important when you're doing this to make sure we're using the correct units and the correct scale. So just take it easy for a second when you pick this up and make sure you got it flipped the right way around when you're measuring something. Couple of definitions for. So the required is desired track. So the proposed path of the aircraft over the ground. So this is what your plan is, right? Required track or desired track. I'm planning to fly to Red Deer. I determine that my track is 015 degrees true or magnetic, whatever we've determined. That's our plan, right? That's our plan on paper. Track made good is the actual path of the aircraft over the ground. It's kind of a bit of a funny term there, but really the only difference, you know, the easy way to remember is our required or desired track is what our plan is on paper. Track made good is what actually happened. Does that make sense? Hopefully that makes sense for you guys. Let me know if it's not hitting home, but you need to know the difference. Need to know these definitions. Track error is the angle between the required track and the track made good. So that like 1 in 60 rule that we were talking about, that's an example of track error, right? So we know that we're a mile off course and we are in error by a degree because we traveled 60 miles, right? So we can use our 1 in 60 rule to determine track error. One of the things we can do. So it's the angle between the required, so what our plan was and what actually happened. The angle between those two is the track error. Bearing, direction or angle from one point to another point. So between me and the IKEA in Winnipeg, what I measure that to be at is my bearing. Okay, so any questions? Oftentimes for bearing, our bearing, like which direction we're pointed, is often 0. So it depends on our bearing is kind of relative to us, right? So if we're pointed, you know, if we're measuring from which direction we're pointed is 0, and then you measure all the way around to where the IKEA is, it might be at, you know, 110 degrees, bearing 110. So we turn in that direction. Bearing is different. Again, that's just when we're actually flying. Track is measured from true north, remember? So we can apply our variation and our deviation to get to what we need, but it's always kind of measured from the North Pole, at least in the Northern Hemisphere. So required track is a plan. Track made good is what actually happened. Track error is our degrees. So remember, it's degrees, it's not miles, it's measured in degrees, the difference between our plan and what actually happened. And then our bearing is our angle from one point to another. Okay, so we're measuring track on a map. Looks like we're going from Saskatoon Airport to the town of Blucher. You know that, so that's the black line that kind of goes northwest southeast. When plotting your route on a map, draw a line from one destination to another. To determine the heading you need to fly, find the meridian that is approximately halfway. So if this midpoint meridian, if that black line wasn't there, you'd be able to see the hash marks on it, right? Just like the other two that are around. The north-south meridians, you can see the hash marks. So you got bigger hash marks every 10, a little bit smaller every 5, and then each individual one is 1. Sometimes you have to look at the scale because it'll tell you. But that's where we're going to measure from. So if we draw a line between the two, we're going to stick our protractor over top of this particular meridian that's in the middle of it, and that's going to help us out. Use that meridian to determine the bearing of the aircraft. So we're going to take our Douglas protractor, like I was saying. So this is called the Douglas protractor, the square. Place that protractor on the meridian with north of the protractor, the north on the map. So north is up. So make sure north is lined up. And then we're going to stick the center of that protractor, that bullseye, we're going to stick that where the track goes right through the middle of it. And then we're going to read it coming out the other side. So remember, this depends on which direction we're going. We're going from Saskatoon to Blucher, right? So we want to measure the track on that particular end towards Blucher, the direction that we're going. If we're going the opposite direction, it would be from the top left. Does that make sense? So it'll give you something like, let's see, we've got 90 there because that's east, so 100, 110, 120. Looks like it's between 120 and 130, about 124. So we're going to find that midpoint meridian. We're going to line up north on that midpoint meridian, and then we're going to put the little hole, the center of that protractor on our track, and then we're going to read it on the bottom end, depending on which direction we're going. So lines of variation, isogonic lines, we talked about that. Determine the magnetic heading. We take the true heading, add or subtract the variation, east is least, west is best. So using the previous example, the true track from Saskatoon to Blucher using the midpoint meridian is 116. And the closest line of variation is 12 degrees east. So let's see, this particular map doesn't really, we can't really see that particular line of variation, so it's a little far. So we have determined our true track is 116 and the closest line of variation is 12. So remember, east is least. 116 minus 12 equals 104. So our magnetic track is 104. Any questions on that? So that's what we measure with our Douglas protractor. Okay, can't really do that. Okay, how's the maximum elevation figure read? And what is the function of the maximum elevation figure? Okay, so our MEF, how do we read this? That 27 up in the top right corner, that's our maximum elevation figure. So what does that mean? What does that translate to? Anybody tell me what that means? Let's see. Drysdale, I haven't picked on you yet. That 2.7 or that 27 that's up in the top right corner of this map, that's the minimum elevation figure. So how do we read that first of all? That 27, or does that mean something else? You might be muted there. Is it 2,700 feet ASL? Yes, so that means 2,700. So big number is thousands, little number is hundreds. So that maximum elevation figure in that particular quadrant is 2,700. I'll see if I can find a better one. Let's see here. So can see it a little bit better in this particular map here. So we've got 3,600, so 3,600 in this particular quadrant of latitude and longitude. So in that box, the maximum elevation figure measured is 3,600. Awesome. What does the area activity code of F represent? Ooh, that's a good one. So let's see. So remember, we're looking at that. We see this on a test. Lots of times we're going to be provided with our VNC. So rather than taking a guess, but just look at the map. So let's see if I can find where F is. There we go. Okay. So we look at our VNC on the legend and we see that area activity code F means aircraft test area. So there's a bunch of test pilots flying around in there. What is the proposed path of the aircraft over the ground? What is the definition of that, or what does that mean? It's there's a definition for that particular term. Does anybody remember? Proposed path of the aircraft over the ground. Riddle.
It's the required track.
Exactly. Yeah, required or desired track. Awesome. All right, conclusion. So we covered 403, 01, 01, 2, 3, and 4. So measuring distance on a map, tracks and bearings, measuring track on a map. So why this is important, you guys have probably caught on to fairly quick why this is important, but you need to know how to measure this in order to plan out cross-country flights. There's a lot that goes into it, right? So you're quickly discovering that before we even get to turn in on our plane and take off, there's usually an equal amount of time and paperwork that goes into it beforehand. You'll have to get to know how to do this fairly quickly. Awesome. All right, radio communication. Slide there, let me know if you can't. Otherwise, we're going to get right into it. So we're going to talk about a government agency that looks after radio communication. We're going to talk about radio waves and how we use them in aviation, and we're going to talk about NAV Canada. So describe ISED. So to regulate and manage radio frequency usage, we need an organization that oversees the allocation of radio spectrum and ensures compliance with national and international regulations. So in Canada, the responsibility falls under Innovation, Science and Economic Development Canada, ISED. So that's what that means. If you see some like old textbooks, or you might hear like one of your officers talk about Industry Canada, that used to be what it was called. It's not called that anymore. So there are current updated terms that have been for probably around a lot longer than you might think is Innovation, Science and Economic Development Canada. They look after radio. One of the things they do is look after radio. Manages the radio spectrum, ensuring efficient use across various sectors like aviation, telecommunications, and broadcasting. They allocate frequencies, so that means like I want to start up a FM radio station for classic rock on 95.7. One of the things I would have to do is ask ISED if there's, somebody on that, does anybody own the rights to that? I would like a license for that. So they look after all of that. Regulate radio equipment to prevent interference between services. So if we have too many radio operators all operating close together on very similar frequencies, it's going to get really congested, right? So they're the ones that look after all of that. What they do for us in terms of aviation, so it works closely with organizations like NAV Canada to allocate frequencies for safe communication between aircraft and control towers. So ensure pilots have access to clear and interference-free communication channels. So the radio, it works differently than your telephone. Telephone, again, you can have a conversation. Both of you can talk at the same time. You're probably familiar, for those of you who are glider pilots already, know that only one person can talk on a radio at the time and everyone else has to listen. Or if you've done an FTX, it's the same thing. If more than one person tries to talk, you get like a squeak, you get like a bunch of interference. So that's what they work to make sure that there's not too many broadcasters in the same. So radio is a wave. It works the same if you were to drop a rock in the lake, it makes waves. It's very, very similar. So electromagnetic radiation is what it's referred to. So if that wave lasted 1 second, the wave passed the same blue point 9 times, thus it was 9 hertz. So it's measured in hertz, which means 1 second. So those orange dots are going to pass that blue center reference dot, goes up and down 9 times in 1 second. So that reference is called 1 hertz. Does that make sense? So that's obviously excluding the, looks like 2, 4, 6, 8, 9. Yeah, so excludes the time at the start. So every time it passes by after that in the span of 1 second is 1 hertz. So this time it happened 9 times in 1 second, so it's 9 hertz. And it's HZ, so capital H, lowercase z. Any questions on hertz, how we measure it? So that's what's called a frequency, radio frequency. Okay, moving on. So you'll see kilohertz, megahertz, and gigahertz on your different equipment. So power line, that frequency is about 60 hertz, right? So that's pretty slow. So it alternates 60 times in 1 second. Radio is 1 megahertz. So like your radio, so for instance, your FM radio in your car, like 95.1 megahertz. For aviation, we use a higher band than that. So it starts at 108. And talking for voice broadcast, the lowest is 118.0 megahertz. A tag reader, 14 megahertz. Television, 50 megahertz. Sometimes your monitors can get like a refresh rate of higher than that if you need. Mobile phone typically is in the 700 megahertz band. Smart meter, like your electrical meter. Microwave is about 2.4. Wi-Fi, if you're using Wi-Fi, lots of them are 5 gigahertz. So the older ones might have 2.4 gigahertz, but most of your Wi-Fi now is about 5 gigahertz. Remote control, tanning bed, X-rays, gamma rays, etc. All away we go. All up to got terahertz, peta, exa, and zeta hertz. So X-rays, obviously, there's a lot of radiation. That's why we don't, the people, X-ray techs and doctors that operate X-rays all day have to hide behind, they have lead clothing because that stops X-rays. And they're kind of behind shields and stuff when they do that. It's not bad, like when you're, if you need an X-ray, like having a couple X-rays isn't that big of a deal, but if you were to like live under that for a while, it's really not great for you. And gamma rays, of course, that's like solar radiation, not good for you. You can see tanning beds on there, right? That's super not good for you. So this, again, it's the same thing. It's just in a picture instead of a table. So you can see power line, and it looks like it's in notation there instead of gigahertz and petahertz and things like that. So 10 to the 7th. So let's see. So you can see radio is at about 10 to the 6th, so 1 megahertz. Then it goes all the way up, terahertz, infrared, ultraviolet, X-ray, and gamma radiation. Spectrum that we're talking about, so radio, we're kind of going back to radio instead of just like everything in life right now. So radio, typically, as we know it, aviation-wise, is generally divided into 3 ranges: low, mid, and high frequencies. So each range of frequencies is known as a band. So you got low band or mid band, and bands are measured in hertz. So you can see low band looks like it's less than 1 gigahertz, mid band is 10 gigahertz, and high band is over top of 10 gigahertz. So that's like really rapid. Low band frequencies are under 1 gigahertz, such as the 600 meg band. Low band radio signal travels the farthest of the 3 bands, and it can travel distances of 10 kilometers or more. Oftentimes it's way more than that. Low band frequencies can pass through walls and buildings, making it possible to bring outdoor signals indoors. So back in the day before cable, when your TV used to have bunny ears to get any sort of reception, so those bunny ears could pick up, even though they're indoors, they can pick up the signal. Due to its ability to cover larger geographic areas and pass through buildings effectively, low band spectrum is well suited to support rural broadband connectivity and varied uses like those of first responders, marine navigation, trucking industry, civil aviation, etc. So the trucking industry, like they have their CB radios, that sort of thing. Low band frequencies are referred to by their sub band names. So we have HF, VHF, and UHF. So high frequency is used for like talking when you're over the ocean kind of thing. So you're a long way from any sort of station. So for me, when I fly from Calgary to Hawaii, once we're out of range of the coast on our normal radios, which are VHF. So typically your VHF is what we use for talking. That's what you also use for listening in your car to like an FM radio station. It's also what we use for most of the time for aviation on land, both for VORs as well as voice. HF is for like long oceanic distance. And then ultra high frequency, that's 300 megahertz to 3 gigahertz. So that's the only people that really use ultra high frequency is the military, and also DME, distance measuring equipment, uses UHF. VHF is where we typically live for talking on the radio. So propagation, another term for like how do they radiate out from their source. So radio waves propagate in different ways. So line of sight, meaning like I'm at 3,000 feet and I can see the Calgary Airport, like I can see the control tower. I can talk to the control tower, no problem, right? Because I can see it. Couple of different methods. However, if something's in the way, so we're behind mountains trying to talk to the Calgary control tower because we're not high enough to be over top of the peaks, I can't talk to them because they're in the way. So line of sight means exactly that. Like you have to be able to see it in a straight line. Otherwise, you're going to have a hard time. Your reception's going to start to suffer. So similar, not too many people listen to FM radios in their car anymore. But if I'm driving to Edmonton from Calgary and I have a Calgary radio station tuned up, I'm going to start to lose it, once I get north of Olds or Red, depending on how strong the station is. But I'm going to start to lose it eventually because the line of sight isn't there anymore. There's also a skywave, so certain frequencies, including HF bands, the high frequency bands, you can bounce them off the ionosphere, like the atmosphere. You can bounce them over top of mountains and things like that. So you can read, so that people a long distance away can read them. Won't necessarily work if you're right behind a mountain, but if you're a long way away, you can get skip wave or skywave, they're called. So we're no longer in line of sight. The other way we can do it is a relay. So for flying from Calgary to Kelowna, we've got some mountains to contend to. There might be a couple of repeater stations on high up on a mountain peak somewhere to be able to repeat that signal so that we can so it's just kind of a midpoint station. So we've got a few different ways that we can do this, right? So we've got line of sight, which is the most common. That's how everything over land typically works, is line of sight. We have skywave, which is that's for super long range talking on the radio, usually only on the high frequency band. And then we have a relay or repeater. So to ensure clear communication between pilots and air traffic controllers, we need a standardized set of phrases. The NAV Canada VFR Phraseology Guide provides specific guidelines for these exchanges. So if you guys want to go onto that first link, I think the first one is the English one, the second one's French that I put in the chat. So if you guys are able to, go ahead and have a peek at that. So write your name phonetically. If you can, keep away from the phraseology guide for this one and just type out your name in phonetics. Hopefully you've been working on practicing on that. That's something that might come up on a selection board or something like that. So go ahead, take a crack at it there. If you need to look at the phraseology guide, that's cool. Let's see, phonetic alphabet is on page 2, so it's right at the beginning, or page 10 on the lat there, but page 2 on the actual document. So go take a crack at writing your name phonetically there if you remember it. If not, have a look at that guide, and then you guys can have a reference to that. Awesome. See a couple of them rolling in there. Awesome. Great work, you guys. Let me know if you guys have any questions. You can see in the phonetic alphabet that they've got some funky pronunciations there, like how you pronounce it. So let's see, Victor is like Victa. They have the emphasis and stuff on it. And the reason they do that, we don't just say, QRST, ABCD especially. Those all sound very similar on the radio, especially if you're talking quickly. So that's one of the reasons why we use the phonetic alphabet instead of just saying the actual letter. Another reason is that when radio was kind of first used for aviation, it was poor quality, right? It's very scratchy, and you can old movies you watch where they're trying to use the radio and you hear lots of interference and static and weird electronic noises in the background. So in order to be heard clearly, you have to make sure you say the phonetic alphabet. Same with the next page on that, and the guide has numbers. So what about how do we say the letter 3 on the radio? Anybody tell me?
3.
Tree, yeah, exactly. Like leaves, like tree. The reason, for whatever reason, when you're talking on the radio, 3 can sound a lot like 7 or something like that. If you were just to say it quickly and not enunciate, the numbers can kind of blend in together, especially if it's kind of mumbled or the frequency is really busy or there's interference. So that's why we have tree instead of, and then same with 9 is niner instead of 9. For whatever reason, 9 can sound like 4. They don't normally in real life when we're face to face talking, but as we talked about in, if you guys remember before Christmas, we did HPMA, like human factors or human performance in military aviation. So a big reason why we have standardized phrases like Roger, or the way we use, for the reason we use phonetic alphabets, or we say numbers the way that we do, like tree and niner, is because most of communication is the nonverbal portion, right? It's the majority of it is, it's not the words that you say, but it's like body language, tone of voice, things like that. That's the majority of communication, right? But aviation's like backwards land for communication because we're not face to face, right? We're always talking to somebody on the radio, even if you're flying with somebody. For those of you that are glider pilots already, you know your glider is behind you, or your pilot, excuse me, your instructor pilot is sitting behind you in the glider. So you can't see like whether they're making eye contact or tone of voice or anything. It's really hard to pick up on body language, right? And it's like that throughout aviation. So that's why we have these standardized phrases. One of the reasons is standardized phrases. Awesome. Phraseology guide. How would we tell air traffic services? How would the control tower tell us that they want us to set 29 or 9 or 5 inches of mercury on the altimeter? I guess I kind of just told you that. So 2 is 2, 9 is niner, so 2 niner, 9 or 5 inches is what they would say. Let's see if they've got something for altimeter setting in here. Decimals, number group, transponder, standard words. Let's see if there's anything in this particular guide here that sells radio check. Maybe doesn't quite look like they have it. Mayday, pan, change to flight plan, MF. Okay, so it looks like they maybe don't quite have it in there, but I told you, I kind of gave away the answer already, unfortunately. So 2 niner, 9 or 5. Let's see if there's, if I search this document, if there's like altimeter, if there's it. Decimal. So 2 niner, decimal, 9 or 5. So the way they want you to say decimal is decimal. So you really kind of exaggerate in the pronunciation. So I'll try not to give the next question away for you guys. Describe a word or phrase that means you cannot do what is requested. So this is an important one, whether you can or can't do it. Air traffic control might ask you to turn a certain direction or climb or descend a certain, but just because they tell you to do something doesn't mean you actually can do it. That's up to you as the PIC, the pilot in command, to determine whether it's safe or not. Who had a Calder? You had your hand up first.
Unable?
Unable is a good one, yeah. Unable is a great one. Yeah, did you have a different example, Nakashima?
Negative.
Negative, yeah. Also potentially can be used in this particular instance. Yeah, absolutely. Great example, you guys. So negative meaning and unable both meaning I can't do it or incorrect, depending on what we're looking for. Awesome. Recommended practices for radio operation. So let's try and find some recommended practices, and guys, pick your favorite one. So it looks like in the sidebar, it'd be page 23. In the actual document, the page number looks like it's 15. So I'll have a quick peek through those. I'll tell you what mine is. Think about and plan what you're going to say before beginning the transmission. So In pop culture, you're familiar with pilots have a tendency to say, like when we're doing announcements to the passengers, this is Captain Steven, and like that. So it's very exaggerated in pop culture, but it has roots in truth. People have a bad habit of not thinking what they want to say before they use the radio. So the way I always say is it's push so that we have a push to talk button. So you push the button and then you speak. It's called push to talk, not push to think, right? That's how I always remember. Is it says PTT most of the time. It says PTT right on the button for push to talk. It's push to talk, not push to think. So think about what we want to say first. Push the button, give it a half a second, and then talk. Finish talking, and then let go of the button. So poor radio etiquette would be not having, what we want to say ready to go. So we're thinking out loud on the air, which is kind of wastes everybody time and it's kind of a distraction. Talking before we push the talk button, so we missed half the transmission, or releasing the push to talk button before we're finished transmitting, so then you miss half the transmission. So that's my favorite one. Keep calls using brief, concise, standard phraseology. Remember that the information being relayed may need to be written down, so speak slightly slower. So that's more for like air traffic control. They're going to give you a clearance and they might speak really fast. You might have to tell them to slow down. Another thing that happens if somebody has a rather thick accent, that you might not necessarily get all their transmission. All you have to do is just ask them to speak slower. That's it. There's no real in and out. But yeah, we're trying to use professional language. So remember, there's fine and it's against the law to swear on the air. It helps if we kind of maintain an even keel. All good points. Awesome. Anything else that stick out to you guys in that particular recommended practices? Nakashima, enunciation is great and conciseness. So we don't want to waste a ton of time. Say what we need to say and then we're done. There's a few people that like to hear the sound of their own voice, and that's kind of a no-no. All right, next question. Explain what it means to have a radio check score of 2. Let's find that section, radio check. Yeah, you bet. So Graphos said readable now and then. So readability 2 is, they might ask you to verify. Oftentimes you'll hear people, they'll say 2 by 2 or 2 by 5. So the first score is readability, and the second one might be volume or clarity. Or volume. So you might hear somebody say, read you about a 2, which means I can understand you now and then, like I'm missing over half of your transmission. Or they might say, I've got you 5 by 5, which means readable and volume is great. So it's perfectly readable and the volume is appropriate. Does that make sense? You might hear 2, which is 5 by 5, or you might just say, I read you a 2. So you just say, Calgary Tower, WestJet 600 radio check, or how do you read? And then they'll say read you 5, how me, something like that. So you can do a radio check, read you 5 or read you 2. And you just say what's coming through. That's important. Good stuff. Any questions on radio check? Okay, next up. That. Let's see. Describe a radio call for a mayday situation where a bird strike requires you to turn around and land back on the runway. So break this down into parts. So how many times do we have to say mayday on the radio? Does anybody remember?
3 times.
3 times. You got it, Brito. Yeah. So we say Calder again. Yeah. Awesome. So we see mayday, 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 right? So that's 3 times. And then we say who we are and what we want. So if you search the document and typed in mayday, it would kind of bring this up. As well, we also have to, so we say Mayday 3 times and then who we are, so our call sign, what happened or what we want. So bird strike, request immediate return. And then you have to say the number of persons, so souls on board and fuel on board. And fuel is listed in endurance. You can list it in gallons or pounds if you'd like, but most of the time it's endurance. So 2 hours of fuel on board. So the example they have is Mayday, 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 Cessna 172 Foxtrot, Oscar, India, Juliet, engine fire, landing field 2 miles southwest of Gander, 3 persons on board, endurance 2 hours. So endurance meaning fuel endurance, how much fuel we have on board. Why don't we say who we are 3 times? It's a good question. I think that used to be what they advise, but now that just kind of wastes time. If it's a Mayday, like you're in trouble and you're in trouble right now. So Mayday, if you say Mayday 3 times, that gets everyone's attention. And then you say who you are and what you want. That gives time for people to stop what they're doing and listen. And then we can pay attention after that. So good question. Difference between Mayday and a pan-pan. To operator certificate, we were told to do that. Okay, they might still tell you to do that, I guess, on that restricted operator certificate. It's a good question. I don't know. In practice, I'm not sure how often that happens. This particular phraseology guide doesn't say to do it, but it might be different for the restricted radio operator certificate. Good question. In my mind, that we already say Mayday 3 times, so I don't know if we necessarily need to say our call sign 3 times, but if that's like in a textbook somewhere that tells you to do that, then I guess that's the correct answer. Awesome. So difference between a Mayday and a pan-pan. Anybody? Very similar, but there's an important difference. Brito, go ahead.
A pan-pan is when it's an emergency situation, but it doesn't require immediate assistance.
Yeah, okay, I'd buy that. Sure, so we got an answer in the chat. Nakashima, Mayday's immediate emergency situation, while pan-pan is more of a concern that is not as significant as a Mayday. Yeah, exactly. So we're both on the right track there for sure. So Mayday, imminent danger requires immediate assistance. Pan-pan is like an urgency. So we're not like an imminent danger, but it's still an urgency message. So in either way, when we land, hopefully we land at an airport, but when we land, there's going to be fire trucks waiting for us. But yeah, Mayday is obviously a lot more urgent. And like it's immediate danger, needs immediate assistance. Pan-pan is like just an urgency message. Awesome. Conclusion. So we talked about ISED, talked about radio waves, and we talked about NAV Canada and VFR phraseology. So, okay, is there any questions on any of that at all that we referred to? That phraseology guide, just keep that in the back of your mind. You can read through it a little bit if you want. If it's a little bit wordy. I guess the last page there is, so remember, if you've not clearly heard a transmission, reply, say again. So say that again, or say again. If you do not understand a transmission, reply, I do not understand. So when you're dealing with like air traffic control and other traffic, if we're not crystal clear on what's happening and who's where, can ask somebody to say it again. It's very important that radio is a tool to use. It's not the only thing we need, but it sure helps to have it when people use it correctly. Awesome, you guys. Okay. It looks like that might be the end of the presentations there. That's all I have for you guys now. Is there anything you guys wanted me to review? I know the next week, I think we have at least one review session, maybe two, I'm not sure, in the next week or two before their exam. So is anybody, for those of you who are, I know it's a school night here, especially for those of you that aren't on Mountain or Pacific time. So you guys are free to go unless there's any other questions. If you guys wanted to stay, I'm happy to review something if you guys had something you needed to review, or if you wanted to do METAR or anything like that. Happy to do that for the next few minutes. Otherwise, the rest of the night's here. Go ahead, Brito.
I have two questions. Can
Sure.
we go back to the radio band section? And also, will we get maps for the exam?
That is a good question. I'm not sure if I don't know how much of it's navigation. I think it's just like an intro. So you would maybe need to know, like, I don't think you're going to be like measuring track or anything like that. It would probably be more like, what is the scale, or what are the four, principles of a chart, like area, shapes, bearings, and distances, things like that. I don't know if they'll necessarily get you to do like a navigation exercise. So that question I'm not 100% sure of. You wanted let's see, this one. Is it this one or is it a different one?
It was this one and a few other slides.
Okay, so this is talking about hertz, so how we measure frequency.
I have this page. Perfect.
Okay, and this one. So talking about kilohertz, things like that. You want this one?
Too.
Yeah, you have that one. Okay, the next page is it's basically just a visible, like a picture instead of a table. The last slide. Then we've got spectrum.
Spectrum is what I'm missing.
Okay, high, low, and mid band. So bands are measured in hertz. And typically in aviation, we use low band. And then within low band, so we have less than 1 gigahertz, it's divided into high frequency, very high frequency, and ultra high frequency. And VHF is where you typically live, like all the radios that are in a glider or the tow plane or anything like that, they're all on VHF. And typically, if you're wondering, so we know how we have like FM radio stations, like in your car or whatever, that goes up to like 107.9, I think. And then after that, it starts at 108. That's like right into the aviation band. And that's for like navigation aids. Up to 118 is where voice starts up to, and then 136, I believe, is the highest. So if you're curious, the aviation band uses AM method in the VHF band.
So pretty much all of aviation is in the VHF band, right?
Typically, yeah, where like our radios that we use to talk to each other, like our airborne radios, are all in VHF, yeah. For voice, I should say. Like our voice radio that we're going to talk to each other on is all in VHF. You got it. Let's see, what else do we have? And then did you have line of sight and skywave and things like that already?
I did not have Skywave.
Okay, so we had line of sight, which is just, where we can see it. Skywave is where you bounce the radio frequency off of the ionosphere. So like off of like the upper atmosphere, right? So it kind of bounces, it'll skip over top of like a mountain or whatever. So we can see, even though we're a long ways away from the station and there's potentially like obstructions and, like mountains or the curvature of the earth is in the way, we can still hear it clear as day because it'll kind of bounce off of the ionosphere. The last one for propagation is like we have a relay or repeater. So it still works off of line of sight. We just have like an intermediate relay station that'll help us kind of bridge the gap so we're not left in the dark.
Can you go back to two before quickly?
Skywave or the one before?
The one before. There's a few details I'm missing, I think.
Line of sight?
Yes.
There, okay, we'll start with this one. Short range VHF communication between airplanes and ground control, and also airplanes and other airplanes. So it uses line of sight. So we have to be able to basically see each other is what line of sight means.
Confused.
Questions on radio frequencies. I don't know, to be honest with you. I don't think so. Maybe the one that they might want you to know is like 121.5 is like the emergency frequency or distress frequency for VHF. Yeah, maybe once you actually do like the Transport Canada exam, maybe. But for I don't quote me on this because obviously I don't know the contents of the exam, but yeah, maybe you should know what like 121.5 is, and 126.7 obviously is en route. But I'm not sure that I don't know that it'll get too much more involved in that. If we didn't cover it in class, chances are it won't be that big of a thing. So Brito, yeah, go ahead.
The exam is entirely multiple choice, right?
I would assume so. Yeah, I'm not 100% sure on that. Again, I think so. Yeah, I think it's multiple choice. I don't actually know the answer to that. I'm sorry. But I would assume since it's a national exam, like there's no like they won't really give you an opportunity to like show your work. So you might have to figure something out, and then it'll list like 4 possible choices, right? So there's no marks for like show your work, I don't think. Again, don't quote me. I obviously haven't seen the exam. I don't make it, but it'll be, yeah, you'll have choices to pick from. Zagrafa, 126.7, that's en route.
What would en route mean in this case?
Like you're outside of controlled airspace. So we're
Okay.
flying from Calgary to Saskatoon. Obviously in Calgary, we're talking to the tower, and then after we take off, we're talking to the terminal because it's really busy. Once we get outside of terminal's airspace in between, we're in uncontrolled airspace, potentially in class G or E. So then we're talking and monitoring on 126.7. So we're not talking to air traffic control, we're talking to other people until we get closer to Saskatoon and we talk to the tower.
That makes sense.
You bet. Awesome. Any other questions, guys?